everyone. In this video, we're going to work through this second example on antiderivatives. Man, see if I can get my brain on track. So I just want to start crunching through some specific examples where we look at a function, we try and find its antiderivative. And I've got this definition up at the top as a reminder. The antiderivative is an entire family of functions. They're all very similar, but it's not a single function. It's an entire family. And what we'll be seeing is that they all just differ by vertical shift. There's other interesting things that can happen if your problem's a little bit different, where we'll be looking for curves that differ by a vertical stretch or something along those lines. We'll see some of that with some differential equations at the end of the quarter, but for now, with the basic antiderivatives, it should be vertical shift. Okay, so again, all you want to be focusing on in this first part of 1.1 is the fact that the antiderivative is the function you would take the derivative of to get whatever it is you're looking at. So if I'm looking at f of t equals negative 1/3, that I'm kind of thinking in my head, that's the derivative function. So we're starting with f of t, and we want to think about going up to what we'll usually call big F of t, but not always. That's not a rule. It's just kind of a convenience. Or if we took the derivative, we'd had a f prime. Okay, so antiderivative if we go up to big F, derivative if we go to little f prime. Okay, so if I have a constant function, and I'm thinking that is the derivative function, that means I have a constant slope. So I'm going to say that I'm looking for a linear function with a constant slope of 1/3. So in this case, I'm going to get something like this. And I'd say what's really important here is that this is going to involve some guess and check, and you shouldn't be discouraged by that. You should just kind of start to think about what looks right, and the way that you always check yourself is by taking the derivative. So if I take big F prime, the derivative of negative 1/3 t is negative 1/3. The derivative of any constant is 0, so this is looking good. Okay, so this is another great chance for you to go ahead and pause and try and work through some of these, and then start back up to see what happens, what I actually get. So if we're looking at g of x equals 2x, again, there's a little bit of guess and check involved, and we're trying to start off easy, so you probably won't need very many guesses. But what I would be thinking here is if I take the derivative and I get an x to the first power, I better have started with an x to the second power. And it's good enough just to make a guess like that and then try your check. If I, what are we doing here, x's. If I take the derivative of x squared, I get 2x. So I'm actually in really good shape already, except that I should throw in my plus c. So that's my answer for B. C is somewhat similar. I'm starting off with this y to the first power right here. So I'm going to guess that I want to see a y to the second power, but I'm sure you can imagine that if 2x wanted a plain old x squared, that a 5y probably isn't going to work from just a plain old y squared. You can still use that as a starting guess. And if I ended up with a constant 3, I better have started with a 3y. And I should have some sort of arbitrary constant. So h prime of y. So this is my check. I'm going to get a 2y plus 3. Parts of that are great. The 2 is not so great right now, so we have to figure out how to deal with that. It's really easy to fix being off by a constant multiple. So here, if I don't want the 2 out in front, then in this problem I'm going to divide by 2, so that over here that would cancel. And I do want to end up with a 5 in front, so I'm going to multiply by a 5. And that will give me exactly what I want, 5y plus 3. So that's the guess and check part of this. It's okay to just pick what you think is closest to the right answer, and then take your derivative and see what kind of correction needs to happen. M of k is just getting a little messier with this, so we're working our way up here to a reverse power rule, basically. So when we're going for big M of k, And we'll say, okay, k to the fourth would have come from a k to the fifth, and we'll just leave some room to mess with constants. K cubed would have come from a k to the fourth, and k would have come from k squared. Okay, and then we can start working on our check. So m prime, right now it would give me 5k to the fourth, and a 4k to the third, and a 2k. None of which are quite right. So now is where we start doing our adjusting. If we don't want to end up with a 5 in our derivative, we're going to divide by 5 here, which will just carry through since it's a constant multiple, so that's looking better. We did want a 2 out in front, so we'll multiply by the 2, and then we'll be left with 2k to the fourth, so that one's looking much better. 4k cubed, what do we want? Plain old k cubed? So in this case, we just need to get rid of the 4, and we would do that by building a 1/4 in to the antiderivative function. So there's our k cubed. And then the last one, we didn't want a 2, so we'll divide out a 2. And we did want a -7, so we'll multiply by -7. Here, we'll go like this, ignore the plus, times, so the 2's will cancel, we'll have the -7k left. So that's looking good. This up here is my answer, right? The green is my check. My answer in blue looks good. Okay, E and F get a little bit tricky, but it's really just that upfront algebra sort of tricky again. So before I even start on big N, I'm going to work on rewriting this a little. So I'm going to rewrite all of the square roots as 1/2 powers. And then if you have an x to the first times an x to the 1/2, you can add those powers and say you have x to the 3/2. And with the 1/x to the 3/2, you can rewrite that as x to the -3/2. Sort of running into my other one. Okay, so that's what my original function simplifies down to. Its antiderivative, I would say if I'm going to end up with an x to the 3/2, I'd better have started with an x to the 5/2. Powers drop by 1 when you take derivatives. And if I'm going to end up with an x to the -3/2, I better have started with an x to the -1/2. Again, just increasing my power by 1. So when I start my check, the derivative of x to the 5/2 would be 5/2 x to the 3/2. Love the power. I don't really like the 5/2 out in front, so I'm going to correct that by multiplying by 2/5, so that when that carries down, I get just x to the 3/2. And when I take the derivative of x to the -1/2, I get -1/2 x to the -3/2. Again, love the power, don't really like the coefficient, -1/2. So to get rid of that, I'm going to go back up here and multiply by a -2. When that carries through, the negative signs will cancel, the 2's will cancel, and I'll have exactly what I want, which is just x to the -3/2. So don't hesitate, just like in Calc 1, to do algebra before you work on the calculus part. If it makes your life easier, then it was a good step, so go for it. F is going to be similar. We're going to have some algebra to do up front. So I'm going to go ahead and firstly, actually you could do this in either order. I'm going to go ahead and square this first. So the bottom's going to end up being a t squared, and the top's going to end up being a t to the 4th minus 2t squared plus 1. And then I'm going to divide the t squared in. So when I do t to the 4th divided by t squared, I get t squared. When I do -2 t squared divided by t squared, I just get negative 2. And when I do 1 over t squared, I just get that, but I'm going to rewrite that as t to the negative 2. So simplifying first gets us back to that basic power rule that we've been playing around with. So I messed with us. I already called this thing capital P of t, so we're not going to be able to use that, so use whatever you want. I'm going to use q of t. There isn't a rule that says you have to do lowercase and capital. It's just sort of a convenience when we're getting started. Okay, so q of t is going to be my antiderivative. If I want a t squared, I better see a t cubed in my derivative. If you can spot the constant right away, just put it in there. I'm just trying to demonstrate a little of this guess and check process. I think I'm pretty confident about negative 2 coming straight from negative 2t. And then if I'm going to get a t to the negative 2, I better have started with a t to the negative 1. So if we start doing our check, we get a 3t squared minus 2 minus t to the negative 2. So we need to fix this 3 and this negative 1. So to fix the 3, what did we actually want to get? We wanted to get a plain old t squared, so we just need to multiply by 1/3, which means we have 1/3 of 3t squared, which is just t squared. And then the minus sign, to fix that, we'll just throw an extra minus in over here. So we'll have 2 minuses coming through when we take the derivative, which will become a plus. So again, algebra before can make your life a lot easier. And then for this last one, this one's actually not that tricky. It's just a recognition thing. People look at that and they'll think they're really stuck. But remember, there are some trig things that are really nice to take the antiderivative of. So I just want to point out that 1 over cosine squared is exactly the same as secant squared. So this that I'm looking at is exactly the same as negative 1/2 secant squared plus theta, which means that our big R better include a tangent. Oh, what I switched to x's on you for? Tangent theta. If I take the derivative of tangent theta, I get secant squared. So if I want that negative 1/2, I actually just have to run it up to the antiderivative as well. And then if I want to get a theta, I better start with the theta squared. Ooh, I'm looking at my last one. Oh, I've been so bad. This last one should have a plus c, and the one before it should have a plus c as well. Okay, back to where I was. So if I want a theta, I should have a theta squared. The derivative of theta squared would be 2 theta, so I'm going to have to throw an extra 1/2 out in front to make sure that that cancels. And this time I will remember my plus c. And again, your check would be, what is r prime of theta? Negative 1/2 just sticks around. The derivative of tangent is secant squared. The 1/2 just sticks around. Derivative of theta squared is 2 theta. The 2's cancel, and that looks great. Derivative of c is 0. Okay, so there's some good examples. Hopefully this is starting to make some sense. Thanks for watching.